Welcome everyone. Welcome to this final edition to the Flower Monthly. It's December the 4th, and as usual, we have our Flower Monthly on the first Wednesday of every month. Today, the agenda is gonna be what's shown on the screen. Now we're giving the short welcome message and providing the agenda. We'll be going through fairly fast through a series of updates we got from the Flower team, updates that are new from the previous Flower Monthly. Then we'll give the floor to Jan. Jan is a research scientist from Flower Labs, and he has been leading the FlowerTune LLM Leaderboard, so he's going to tell us everything about it and the latest updates. And then we'll get two super interesting talks from two PhD students. The first one is Jan. He's joining us from Ikerlan, and he will be talking to us about his latest work on vertical federated learning. And the second talk will be given by Luca, also a PhD student, and he's going to tell us how to balance some of the concepts, some of the hottest concepts in federated learning, which are privacy, utility, and fairness. So without further ado, let's begin with the Flower updates. And as usual, you can ask your questions directly on the chat here in Zoom, and I will be answering live. So Flower update, just like we announced in the previous Flower Monthly, one of the biggest events of the year is the Flower AI Summit, which is taking place at the end of March in London. It's going to be a 2-day event. First day is going to be about research. You will get to learn everything that's new with federated AI from the top researchers in the world. And the second day, you will learn how the leading companies are already using Flower to deploy their federated learning and federated analytic use cases. If you haven't registered already, registering is super easy. You can go to the flower.ai website and find the link there, or you can just scan this QR code and it will take you to the registration page. If you have been doing something cool with Flower or federated learning in general, we are inviting you to, of course, to show up in person or online, but also we're inviting you to submit a poster or even a talk if you wish to present something in the Flower Summit. Updates regarding the framework, we have quite a few, even though the last time we were here was just 4 weeks ago. We have released Flower 1.13, and soon after that we made some smaller updates with features that didn't make it to the main release. Flower 1.13 includes a big change when it comes to deploying apps using Flower. Two of the main entities in the infrastructure layer that are the superlink and the superexec, now they have been fused. Everything runs inside the superexec. There has a major update going on in the documentation, updating pretty much all parts of the documentation and adding new pages relevant to the recent changes in the infrastructure layer of Flower. We have a very much improved Docker support. Now Flower uses NumPy 2.0. That was a long requested features by some of people doing data science analysis. Many of them rely on the new functionality that's only supported in NumPy 2.0. And as I said, major updates to the deployment engine, and many more updates under the hood that you can find more about them in the associated blog post, like this one, that you can find directly linked in our website. There were some smaller updates to Flower datasets, but one of the big updates was the announcement of this blog post that came out actually today in the morning. In this blog post, we analyzed over 150 papers from the top conferences, which are ICML, ICLR, and NeurIPS. And we were quite surprised to see that over 75% of the datasets that are included in all these papers are only used once. What does it mean? It means that comparing different papers, different algorithms between each other becomes very difficult when there is when the same datasets, even the same FLS scenarios, are really difficult to replicate across multiple works. So go take a look at this paper because you will find some interesting insights. And also, quite importantly, you will find how you can take pretty much all of these datasets and start using them in Flower datasets. Again, about Flower datasets, we have added two quite important documentation pages that will show you how you can contribute a dataset and make it available to the Flower datasets ecosystem. And also we have a table of the thoroughly tested datasets that are available in Flower datasets. As we have been mentioning other times, there is really nothing stopping you from taking any dataset in Hugging Face, which are by now more than 200,000, and using them in Flower datasets. But those that we have verified and more carefully are listed here. I believe there are close to 50 from different modalities, not only image datasets. Finally, we have been creating some pretty detailed and interesting industry pages where we showcase how federated AI can be useful in a variety of modalities, like the automotive sector and finance. You can find them following the links here. And also, coming very soon, there will be another page that shows what are the most relevant use cases for federated AI in the IoT ecosystem, whether it is running federated AI in devices in the home or in places like factories. So I believe this is everything from the Flower update. If you have any questions, you can reach out to us on the social media channels that we have, or you can ask your question in the chat here in Zoom. So with that out of the way, I want to open the floor to Yang Gao. He's a research scientist in Flower Labs. And among other things, he has been leading and really putting together everything about the FlowerTune LLM leaderboard, which is a very interesting competition about LLMs, but I'm not going to provide any details now because Jan is going to tell you everything about it.
Yeah, thanks, Javier, for the introduction. And yeah, I'm Yan, a research scientist at Flower Labs, and it's a great opportunity here to give a brief update of the our Flower initiative, FlowerTune LLM leaderboard. So, but before that, let me just briefly give a recap about what this Flower initiative is. So, FlowerTune LLM leaderboard is a Flower initiative of obviously is a leaderboard which ranks the federated fine-tuned LLMs trained on the distributed data using Flower. But more importantly, so why we want to do this initiative. So as we all know, the LLMs got remarkable performance across different domains and machine learning tasks, but it also faced some challenges. So the first will be some evidence have shown that we are running out the high quality public data sets, which are required to train the LLMs. And the second, the need of this domain specific knowledge for training the LLM for LLMs, fine-tuning the LLMs is increasing. And yeah, we know that we can't directly access to the protected data, for example, from the medical domain or finance domain. So federated LLM fine-tuning provide a potential solution for this, and it achieve like collaboratively training the model without compromising the user privacy. But again, it still faces some new challenges coming from the both federated side and also the LLM tuning side. So this Flower initiative is trying to build up a unified benchmark that everyone can easily use that. And on top of that, they can build up their own method. And of course, we also encourage people to contribute to this domain, and we hope that we can like work together to build up the future of federated LM fine tuning. Yeah, so in this initiative, the FlowerTune LM Leaderboard, we currently have 4 challenges. It's involved different domains, including the general NLP, finance, medical, and code, the programming. And after it launched, we got numerous people interested in this activity and ask many questions. And also we have already got many submissions. And I'm currently working on like reviewing the different submissions. And also some of the excellent submissions already finished the review and upload to the leaderboard. So now let's just showcase some excellent examples in the medical challenge. So let's move on to the website. So here you can see the medical LM leaderboard website. We have merged a few good submissions. Yeah, so let's first look at the one from the Gaussian cognitive computing lab. So let's click to the code link. You can jump to the GitHub rep they have. Yeah, so the main change they have done is instead of using the original Mistral 7B model, they switch the base model to a more advanced and more specialized for the medical domain, so which is the biomedical Llama 3 8B. So after that, they also found that even they trained the LMs for 10 FL rounds, it can get a remarkable performance. And you see that it's got a big jump compared to the baselines if you compare these 2 numbers for the average performance. That's great. And another submission I want to show is from an individual contributor. His name is Massimo. So let's take a look for that one. Oh, sorry, I guess. Oh, yes. So for this submission, they also change there's 2 main changes they did. The first is they also changed the base model from the default Mistral 7B to the Q1 7B instruct model. And apart from that, he also tried with like different hyperparameters. So for example, they add the warm-up steps for the fine tuning at the first a few rounds, and also they changed the aggregation strategy from the Fed average to Fed prox, and yeah, with that's motive and some others, and I don't want to mention details here, but with all of them, they achieve better performance with even 100 rounds. So you can see the a small training loss dropped down here, and the performance of course is also better compared to the baselines. Yeah. So just in summary, I want to say that maybe some people get scared about so that they don't have like the published paper and don't have the fancy algorithm to participate in this leaderboard. But don't worry about that. I would say, of course, if a published paper are welcome to be submitted to this leaderboard, but you can also like make just a small contribution, make a small step to this area, and it's good enough, and it can be merged into this leaderboard. And also, apart from the model performance, we also consider like the model size and also the communication cost and for example the memory cost for the training as well. Yeah. So if you haven't started your work, so it's easy to participate. So that's just the 4 steps. So one, just choose the latest challenge that I mentioned, and just design after that design your own methods on top of the provided template code. After that, evaluate your model using the provided evaluation metric. And after that, just submit it. Yeah, so just feel free to scan this code to join the Flower Slack and jump to the FlowerTune LM Leaderboard channel, and we will keep the latest news with you. Yeah, we are looking forward to your submissions, and yeah, let's work together to make more contributions to this area, the federated LM fine-tuning. Thank you.
Thanks, Jens, for the great overview. Can you maybe show in the website how to where can people find the instructions, for example, to participate?
Yes, sure. So if you go to the Leaderboard website, so here, after that, so you just go a bit down and you can see panels here, how to participate, and click read more. Then we'll jump to this block to show the detailed steps of how to participate. And you could just, follow these instructions here to start your work and submit your job.
Okay, cool. Perfect. Thank you very much for the update, and it's great to see some already pretty good submissions in the medical leaderboard. Okay, if there are no questions, let's jump to our first guest speaker. I'm gonna share my screen briefly. So our first speaker is going to be Johnny Rureta Berrena. He's a PhD student from Ikerlan, which is a research center in the Basque Country in Spain. And he's going to be telling us all about his latest research, which he's titling Towards Active Participant-Centric Vertical Federated Learning. I think this is a very interesting piece of work, and looking forward to learn all the details. So the floor is yours, John.
Thank you for the introduction, Javier. So I will go ahead and share the screen. Well, so as Javier has said, I'm Johnny Dudeta, and I'm a first-year PhD student at Ikerlan Technology and Research Center. So today I'll be presenting our latest work in federated learning, which is entitled Towards Active Participant-Centric Vertical Federated Learning, Some Representations May Be All You Need. This work is the result of a collaboration with the University of the Basque Country. Before getting into the technical part, I would briefly like to introduce what Ikerlan is. So Ikerlan is a research center that is located in the Basque Country, as Javier has said, in the north of Spain. And we do have offices and labs in different cities, such as Bilbao, Hernani, and Mondragon. But Ikerlan is part of the Mondragon Corporation, which is a corporation that is composed by 268 companies and has more than 73,000 employees worldwide. But what do we do in Ikerlan? Well, so we do have 3 main lines of work that are digital technologies and AI, embedded electronic systems and cybersecurity, as well as energy and mechatronics. So I'm part of this first section, and in here we do have 2 main subgroups that are distributed and connected intelligence and artificial intelligence and data. Me, myself, I'm developing my PhD in the AI team, but as you can see, we do have some other teams that work in closely related topics. So with that being said, let's get into the technical part. This is the index of today's presentation. So I would like to start by introducing vertical federated learning and trying to clearly define the problem that we are trying to tackle in our work. After that, I will talk about our proposal, APC-VFL, which stands for Active Participant-Centric Vertical Federated Learning. And I will close the presentation with some experiments that we have performed, the results that we have obtained, and conclusions and future work. Well, so let's get started. So I won't get into what federated learning is, nor why it should be used, but I will start by talking about different types of federated learning, right? So these different types can be defined based on the data partition between participants. So we can either have horizontal federated learning, which is the typical one. Most of the people do research in this field, but vertical federated learning also exists, and I will focus on this second one. So vertical federated learning, as the name shows, means that we have a data set that is vertically partitioned between participants, as we can see in this figure over here. So that results in a scenario where different participants have distinct features about some common samples. Since the data set is vertically partitioned, we do also assume that there's a single participant that has access to the labels, and this participant is known as active participant. But it is unable to train a good classifier to predict those labels on its own. And because of that, it does require some help. And the ones that help the active participant are the passive participants. And this is pretty much the vertical federated learning setup. And taking this into account, I would like to start by explaining a classical vertical federated learning approach, which is a vertical split NN. So to understand how it works, let's assume that we have this scenario over here where we have 3 different participants. So vertical split NN requires each participant to have a local encoder or a local feature extractor, and then the active participant must also have a classification header. So how does the forward pass work? Well, each participant must get the embeddings, the representations of the batch, and send them to the active one. The active will aggregate them all, ideally by means of concatenation, and then it will perform the predictions using the classification header. As we have previously defined, the active participant does have access to the true labels, and because of that, it will be able to compute the loss and update this classification head with regular gradient descent. After that, it will have to compute the gradient with respect to each one of the local outputs and send it to the corresponding participant. On that way, we can also update these local feature extractors. So even though this is like a pretty logical approach to tackle or to face this BFL scenario, this vertical split NN and the other classical BFL algorithms have 2 main issues. Those are that, first of all, they do require to exchange a lot of information between participants for the training. Because as we can see here, for example, per batch, each participant needs to send the representations of the data to the active participant, and then it does also need to get the gradients. And then another issue, which may not be that straightforward to see, but is a really big issue, is that they are limited to the usage of aligned data. So what is aligned data? Well, we see that a sample is aligned among participants if and only if every participant has information about it. So for instance, if these 3 participants were 3 hospitals, we will see that a sample, that is a patient, is aligned among them if that patient has visited all the hospitals. But it is easy to see that that's such a big assumption, and it won't hold in most real-life scenarios because the sample space won't be the same for every hospital or every participant, right? So I would like to follow by showing you what a real BFL scenario looks like for a 2-participant case. So we will actually have some samples that are aligned between the participants, right? This subset DA. I like calling it the classical limit because those are the samples that can be used by the classical algorithms for training and for inference. But we can also see that there are some data blocks that are not aligned between participants, right? So here the big question is like, can we somehow use this data? Can we incorporate the knowledge of this data to the training process? And what's even more important, can the active participant do the predictions of these non-aligned samples, right? So taking into account these main limitations or these main problems of classical vertical federated learning, our proposal or our approach has 2 main goals. So with our approach, what we want to achieve is flexibility and efficiency. Flexibility, why? Well, We don't want to be limited to the usage of aligned samples for training nor inference. And we do also want our approach to be efficient in the sense that we want to reduce the required communication runs as much as possible, because if this is high, there can be some issues in real scenarios when participants have communication issues. So how do we aim to achieve this, or how do we aim to tackle the issues of classical BFL? Well, with our approach, APC BFL. So in here, you can see the general overview of our proposal, which has 4 different steps, but I like dividing it into 3 main blocks. So the first block would be the first 2 steps that are the federated steps. We will see in a second how we do this, but the goal in here is to learn a joint representation of the aligned samples. And what's the most important part in here is that we require a single information exchange between participants, which is carried out in this second step. After that, the federated part is over, we can say. Because in the third step, what we do is we do knowledge distillation to transfer knowledge from a federated model to a local model. And then in a final step, we train the classifier. Here, it is important to mention that in order to train the classifier, we will use the whole data set of the active participant. That is, we won't be limited to the usage of aligned samples. Therefore, we are able to achieve the aforementioned flexibility. So being this a general overview, I would like to go a bit more in depth into each one of these steps so that you guys can understand which was the thought process behind it. Well, so in the first step, what we are aiming to do is we are aiming to learn the representations of the data of each participant. So for that, what we need to do is we need to train these encoders over here. So the question that we need to answer is, how can we train these encoders, right? So we want to be able to train them without using labels. Why? Well, as I have said before, the active participant will have access to some labels, but the passive won't. And we wanted this first step to be identical for every participant. Because of that, we chose not to use labels in it. So taking that into account, the most logical approaches could be using contrastive losses or using autoencoders. Some people may think that we should go for contrastive losses because they are super popular in self-supervised learning, but it must be noted that our approach focuses on the tabular domain, and they aren't that well known for tabular domain. Because of that, we chose autoencoders. So basically, the idea in this first step is to train these encoders, but locally, without exchanging any information between participants. On that way, what we are doing is we are giving more weight to the local training and making the process more efficient. Once we have these encoders trained, in the second step, the idea is that every passive participant should send the representations of its aligned samples, and only the aligned ones, to the active participant. This one will concatenate them, and by means of another encoder, will get a joint representation of them. So, as we chose autoencoders to train these encoders of the first step, so do we in this second step. And G2 is nothing but the encoder of another autoencoder. So having this trained, the federated part is over, as I have said before. Because now what we do is we do a knowledge distillation process, where we somehow aim to transfer the knowledge from this federated model to a local model. And we do more precisely feature-based knowledge distillation. Why do we do it? Well, the goal is to guide the training of this autoencoder of the third step, because this autoencoder will be trained using only the samples of the active participant, the whole dataset, the aligned and the non-aligned ones, but it will only see active participants' data. So how do we try to guide the training? Well, we try to guide the training with the following loss function, which depends on the type of data that is being processed by the autoencoder. So in case that the data point is not aligned, we don't really have any extra information about it, right? So the loss function is the reconstruction error of the autoencoder. But on the other hand, if the data point is actually aligned, that means that we do have some extra information about it. Which is that extra information? Well, the joint representation that we learn in this second step, which is a representation that gathers the information that every participant of the federated process has about that sample. Therefore, In that case, we have a compost loss function, which is the reconstruction loss plus the distillation loss. So here the idea is that on those cases where a data point is aligned, what we say is that, well, the autoencoder shouldn't only give a gut reconstruction, but it should also be able to generate a representation of the data that is similar to the joint representation of the second step, which is a much more informative representation. So what we argue is that by guiding the training of this autoencoder, G3, this encoder, is able to give us enhanced representations that have been enhanced by the federated process. So the final step is the most straightforward one. What we do is we simply take this final encoder and we get the representations of the whole dataset of the active participant, which can be seen as some alternative dataset. And using that alternative dataset, we train the final classifier, which can be any machine learning or neural network. So that's what we propose. So now I would like to explain which are the experiments that we have done and the results that we have obtained. Well, so we have done 2 different sets of experiments. We have used 2 different tabular data sets, and we have tested everything in vertical federated learning scenarios with 2 participants. The first set of experiments is the set of experiments that we do in a real BFL setting, that is, without fully aligned data sets. There, we do compare our approach with different baselines, being the first one a locally trained model, a model that the active participant will regularly train. Then the other baseline is another locally trained model, but in this case, we train this model not with the regular dataset, but with a transformed dataset. How do we get it? Well, so the idea is that we train the autoencoder of the third step, but we do not apply any sort of knowledge distillation. And once we have it trained, we get the alternative dataset and train the local model. So this is a super important baseline because this can be seen as an ablation study, because this will show us how effective the knowledge distillation process is. And then the final baseline is BFET trans, which is another state-of-the-art BFL method. Then in the second, and in here, we do generate different scenarios by varying the data partition. That is, by varying the amount of features that each participant has access to. And then in the second set of experiments, we do assume that the datasets are fully aligned, and we do also assume that the scenario is ideal in the sense that there is not any sort of information loss during the training process. And under that scenario, we compare our approach with vertical split NN, which is the first algorithm that I have explained. So notice how, when we assume that the datasets are fully aligned, the knowledge distillation process doesn't really make much sense. Because of that, we do modify our approach, and what we do is we train the classifier on the joint representation of those aligned samples that we learn in the second step. With this, what we do is we aim to evaluate the effectiveness of local training using those autoencoders. And in here, we do not generate different scenarios by varying the amount of features that each participant has access to, because the training and inference is done in a collaborative fashion. Here we do vary the number of aligned samples, which is equivalent to varying the dataset size, because the datasets are fully aligned in this case. So which are the results that we have obtained? Well, in the first dataset, which is Mimic3 in the real scenario, what we can see in here on the x-axis are the different scenarios, and in the y-axis we have the F1 score. We chose the F1 score because Mimic3 is a multi-class classification task without fully balanced classes. So the blue line shows the regular local model trained by the active participant. The purple one is the other state-of-the-art proposal. The yellow one is the ablation study, that is the local model that we have trained with transform data, and the other 2 curves, the green and the red, are the result of our approach. So what can be seen here is that our approach does outperform the other alternatives, but what's truly interesting to see is the difference that there is among our approach and this yellow line, because this is the difference that knowledge distillation is doing. Therefore, we can see that it is worth doing this knowledge distillation process and the federated learning part. Then in the second dataset, which is breast cancer Wisconsin, a binary classification task, what we can see is identical. Our approach does outperform the other alternatives. And there's especially interesting to analyze the difference that there's between our approach and the yellow curve. Then, when it comes to the comparison with split NN under the ideal classical setting, in the first dataset, MIM3, what we can see in the first column is the dataset size, that is the amount of aligned sample. And in the last column, what we can see is the communication rounds among participants that were needed for the training process. So what we can see in here is that when the dataset is relatively large, split NN does actually have an edge over our approach. The performance is better, but it does require to exchange much more information. But when the dataset size gets smaller, that difference does also get smaller, and it gets to a point where our approach does outperform split NN while being much more efficient. Then, in the second dataset, breast cancer Wisconsin, what can be seen is that the results are pretty much equivalent in every scenario, but in the last one, where our approach outperforms split NN. So, being this the results, just to finish the presentation, I would like to make some sort of quick summary as final conclusions, and I would like to mention a couple of interesting future working lines. So, well, in this work, we have developed a new VFL method that requires a single information exchange. That is, we achieve that goal of efficiency that we have set in the beginning by reducing to the maximum the amount of communication rounds between participants. And we achieve that by combining local self-supervised learning, in this case, using autoencoders with a knowledge distillation process. And we also see that this approach is flexible in the sense that it is not limited to the usage of aligned samples for training nor inference. When it comes to the experimental results, what we have seen is that in a real VFL scenario, it does outperform other alternatives. And then when it comes to the comparison with vertical split NN, which has been carried out in an ideal classical VFL scenario that is fully aligned dataset and no communication issues when training, what we can see is that there are certain scenarios where our approach does get equivalent results by being much more efficient and flexible. Because even though we have done the comparison in this ideal scenario, our approach is not limited to it. When it comes to the future lines of work, there's a lot of work that has to be done still in the field of VFL, but closely related to our work, we think that it will be interesting to explore alternative representation learning methods because our approach does not work in the feature space, but it works in the representation space. So we think that by having better representations, the overall performance will be enhanced. And finally, we also think that it will be interesting to extend our work to scenarios where participants have, for instance, images instead of tabular data, or even multimodal scenarios where each participant will have a different modality. So that was all. Thank you very much for your attention. And now, if you have any questions, I will do my best to answer them. But also, here you have my email address. So feel free to send me a message. So thank you very much to the Flower team and especially Javier for inviting me here and giving me the chance to share our work. Thank you.
Okay, this was a great talk, John. Thank you for providing the details and also the ideas on how to take this work further. So while the audience thinks for some questions, I have a couple of questions that I would like to ask you. So the first one, which I wrote just as you were finishing your presentation, is, well, you are working with tabular data, but then the moment each client and the active and all the clients participating, the moment they pass their data through the encoders, then there is no, at least from what I can understand, there is no machine learning component that is specific to tabular data anymore.
That's it. Yeah, that's it. I mean, you are, at the end of the day, what you're doing is you are working in this, then share the whole architecture. So you mean in here, right? Like once you go through that encoder,
Yeah, once you enter into phase 2, everything is encoders. But it could be machine learning modules and stages that could be perfectly used for other type of data that is not tabular data.
yeah, that's it. So in here, just by adapting the architecture of these models in here, you could adapt the proposal to any other modality in principle. So you could work with images, for example, if these models are convolutional networks.
But do you think there would be value in, given that the data, it is known that it's tabular data, and there are so many forms of processing tabular data that work better than, for example, I'm thinking about, random forest or XGBoost. It
Yeah.
works better in general with tabular data than passing it to a random CNN.
Okay. Yeah. So that's the thing. I think that will be interesting in here, like in the final step.
Yeah.
You are free to use like a random forest or a tree-based algorithm, XGBoost. You can use whatever. So the idea of our approach is to somehow be able to generate this enhanced data set, which is beneficial for the final classifier. But then the final classifier, we do not limit that. You can use whatever you want. So you could do a grid search and find the best classifier. You could do your test, and you could just choose the one that performs the best.
Mhm. Can you give some maybe brief details on what machine learning model, like the black box, which ones
Yeah.
do you use?
Okay, so in our case, the results that we share in the paper are based on logistic regressions because we were aiming to do some sort of linear probing, like what's done when you evaluate self-supervised learning approaches. So, because what we were aiming to do is to evaluate the quality of this data set. But we have also done tests with trees and super vector machines, and we see that it does work as well.
Thanks. One other question. So you have here several stages, and as you were mentioning, once the passive clients have communicated the embedding back, they are out of the picture, but still there are 3 more stages. Have you considered doing steps, 2 to 4 end-to-end?
2 to 4 end-to-end.
End-to-end by that
Yeah.
I mean, include the final labels and the black box into the distillation, for example, as well.
Yeah, I mean, that's actually something that we are working on currently when we are trying to adapt this approach to the image domain. We are working on something like that. But yeah, you could definitely adapt this and train it end to end. Yeah, like you could have a loss function that will be like the cross entropy of the final classifier plus some sort of distillation loss. Yeah, you could definitely do that. And that's what we are working on currently.
Very interesting. Yes, final question. Could you give maybe from the top of your head some real world examples where, taking into account also the unaligned data could be useful?
Yeah, I mean, I will say that not only useful, but it's a must. Because let's say that you have this setting, right? And let's say that you go for only the aligned samples. So you, as active participant, you never want to train a model that you can only use for a subset of your data. So you will never say a bank, okay, I can try to help you train a machine learning model, but you will be able to use it only with some clients. And the condition would be that client having a bank account in another bank as well. So because of that, it's actually a must being able to use non-aligned samples in order to apply BFL in real scenarios. Because in academia, yeah, it's just fine if you are limited to the usage of aligned samples and you can do some really nice stuff. But if you really want to use BFL in real world scenarios, you need to be able to use non-aligned samples as well.
Okay. Yeah, I mean, this sounds like a pretty convincing answer on why we should take a close look into your paper and implement algorithms based on that. So, okay, I don't see questions at the moment, so I think we can thank you once more for the fantastic talk, and we can proceed to Lucas' talk.
Thank you.
Thank you very much once again.
Thank you for inviting me.
Yeah. And if anyone in the audience is interested in this work to learn more, feel free to reach out to John. So our next guest speaker is Luca Corbucci. He's a PhD student in computer science at the University of Pisa in Italy. And he's going to be talking us about his latest work called latest completed work. Probably there are other things happening called PUFFLE, Balancing Privacy, Utility, and Fairness in Federated Learning. And really interested about this work. I had the chance to go through the paper very quickly, so I hope to get a complete overview of what it is about. So the floor is yours.
Thank you for the introduction. Can you see my screen now?
Yes, we can see it.
Okay, perfect. So, thank you again for having me today. I will discuss about my latest paper, PUFFLE, Balancing Privacy, Utility, and Fairness in Federated Learning. I'm Luca Corbucci, and I'm a PhD student at the Computer Science Department of the University of Pisa. This is a work that I've done during the period that I spent abroad during the PhD. I visited the Telefonica Research Lab in Barcelona for 1 year, and this was basically the results, a part of the results of that period that I spent there. So I did this work with my co-authors Mikko Aikila, David Solanzo Nuguero, Anna Monreale, who is my supervisor on the University of Pisa Sci, and Nicolas Curtellis. And so, to start, I will introduce a little bit the problem that we wanted to solve, starting with talking about these three trustworthiness requirements that I mentioned in the title of the paper, that are the privacy, the fairness, and the utility of the model. In the literature, when we started to work on this topic, we found that there are a lot of works that are already trying to solve the problem of training maybe a model that is fair or a model that is private. We couldn't find any paper that mix all these three different requirements. And so we tried to stay in the middle of these three circles, basically. And I want to introduce a little bit these three requirements. One is the fairness. When we talk about fairness in machine learning, we want that a model that we train treats every different groups in the same way, like fairly. So basically, when we predict something, we don't want that this prediction depend on some sensitive attribute that can bias the model in some way. So if I want to make a prediction, I don't want that this prediction depends on some attribute like, I don't know, the gender or the country of that specific sample. And there are a lot of metrics to understand how fair a model is. In particular, we use the demographic parity, but I want to highlight that the entire methodology that I will present can work also with other fairness matrices. We tested with this one, but it can be used also with others. The only requirement is that these metrics should be differentiable. The second thing I want to introduce is the privacy in machine learning. When we talk about privacy in machine learning, we usually talk about the goal of releasing a model that can be used by users, and these users shouldn't be able to infer any other information about the training data and shouldn't be able to infer new information that they didn't have before starting using the model. The main approach that is used to ensure that a model is private is the use of differential privacy. And in particular, this can be used using the PSGD algorithm that is implemented in some different libraries. In particular, we use one library that is called Opacus. And the last thing, when I talk about utility in this paper, we mean the model accuracy. I think I don't need to introduce federated learning here. Just one thing to simulate. We simulated a federated learning scenario in all the experiment that I will discuss later using Flower, and I will talk more about the experiment and different setting that we consider in the next few minutes. So before going to our solution, I wanted to highlight a little bit the different limitations of the current solution that we found in the literature. So the first thing that we started like trying to understand what were the solutions that allow us to train models that can be fair. And the first thing that we notice is that most of these solutions are basically only for a centralized learning scenario, mostly because they were originally developed for that scenario, and they are not directly applicable in a federated learning scenario. And this is because of how the data are distributed. For instance, for some of these solutions, you need to compute some fairness metrics during the training of the model. But if a client, for instance, has only samples from one group, you cannot compute this fairness metric because you don't have all the others group and you don't have the metrics from the other groups. And this is a problem that we solve in the solution that we propose. And the other problem that we found is that most of the solutions only tries to ensure either the privacy of the model or the fairness. And mixing these two things is not that common. Was not that common in the literature. There is the third problem that we found is probably the biggest one, because one limitation that we found is that when you train a model and you use one of these metrics, one of these approaches that are available in the literature to reduce the unfairness, the main problem that we found is that you don't know in advance how fair or unfair the model will be at the end of the training. So you just apply the method and hope that it will work. And this, in our opinion, is a limitation. And connected to this problem, there is another one that is that most of these solutions, and especially the solution that propose to do some reweighting, like giving more importance to some samples and with respect to others, they only offer a limited reduction of the unfairness of the models. So given all these limitations, we started developing PUFFLE. That is our solution. It's an easy-to-use solution that allows to train a federated learning model that can guarantee privacy and a certain level of fairness, while without decreasing too much the model utility. Just to give a quick overview of the methodology, I want to start introducing one requirement and one preference that the user of this approach has to set before starting using this approach. So basically, one is a requirement because it's related with the privacy. So before using this method, basically a practitioner who wants to use this method has to set the upper bound on the privacy risk that wants to tolerate. So this is, since we use the differential privacy, we ask the practitioners to set just the epsilon that he wants to guarantee at the end of the training, and instead, and this is a strong guarantee, because at the end we will just say, okay, this is the model that we train, and we guarantee that this is the epsilon for the differential privacy. On the other side, we have the fairness preference. This is a target value for the unfairness that we would like to have in our final model. This is not a strong guarantee like the differential privacy is, but in our experiment, we have seen that basically in all the experiment, our model at the end of the training is really close to this target. Sometimes maybe it's a little bit above, sometimes below, but we are usually close to this target. And this depends a lot on the distribution of the data on which you test the unfairness, basically, because you train on some data, and if the test is really similar, the behavior of the fairness will be similar, otherwise will be a little bit different. Our approach is based on our regularization, because we basically we compute this regularization term during the training, and then we use it to reduce the unfairness. And probably the biggest news, the biggest part of this work was the introduction of a tunable approach, because and this is connected to the fairness preference, because based on the fairness preference, the methodology is able to adapt itself to guarantee the privacy and the fairness. And I will talk a little bit about this part in a couple of slides. About the reduction of the unfairness, as I said, the methodology is based on using a regularization term. So we use the regularization, and for each batch we compute the unfairness of the model, and we use this unfairness as a regularization term. We compute the gradient based with respect to this regularization term and with respect to the classic model loss, and then these two gradients are summed using a weighted sum. And the weight in this case is a parameter that we call that is called lambda. In a previous paper that we cite in our paper, this lambda is a fixed value, while instead we introduce the concept of a tunable lambda that can change during the training. About this tunable lambda, this is probably, I say, the biggest part of the paper, because it's with the tunable lambda we extended the state of the art, the methods that were already available in the literature. Basically, this methodology, the idea of this methodology comes from the idea of having a target unfairness level. So the practitioner, as I said, has to set a target unfairness level, and based on this target, our method PUFFLE is able to compute the corresponding lambda that is able to that is then used to sum the two losses. So when the model is really unfair, the lambda will be higher, basically, and the higher is the lambda, and the more is important that we give to the reduction of the unfairness. We believe that giving the possibility to just pick a target unfairness level instead of saying you have to decide which lambda you want to use is a method that is easier to interpret, because you don't need to know what's the meaning of the lambda, but you just need to understand what's the metric that you are using to measure the unfairness and what's the level that you want to use in your model, that you want to have in your model. About the experiments, we tested our methodology on 3 different datasets. 2 of them are tabular datasets. One is an image dataset. So for the image dataset, we used the CelebA dataset. So it was a face recognition task. The important part here is that to train a model and to measure the unfairness in this case, we couldn't have just an image, but we also needed some metadata. Like for instance, for each of the images that we consider in the CelebA dataset, we also had some metadata about the content of the image. Like as far as I remember, we used the gender as a sensitive attribute. So for each image, we also knew the gender of the face in the image, and we also had some other metadata that we didn't use. For tabular datasets, it's easier because you already have some sensitive values inside the tabular datasets, and in particular, we use Dutch and a version of ACS income that is like an adult dataset but bigger. And in terms of number of clients, we use 150 clients for the image dataset and for Dutch, while for income, we used a real-life distribution in the sense that this dataset is already split into 51 clients. And because each client basically is a state of the United States of America. And we tested 2 different levels of privacy for each of the datasets, and we tested 5 different fairness targets to see how is the trade-off between the different targets? Like I was saying before, that the more you decrease the target, the more you have to increase the lambda, the more is the importance that you have to give to decreasing the unfairness with respect to increasing the utility of the model. And the last thing, we did 2 studies. On one side, we studied the global unfairness of the model. So the unfairness of the aggregated model, basically, computed on the server side using some statistics coming from the different clients. And on the other side, we also studied the local unfairness of the different nodes. To compute the unfairness of the aggregated model, the different clients shared some statistics about their predictions, and these statistics are also differentially private to preserve the privacy of the users. So I have some results to show you. I want to start with this one. In this case, we are considering the Celebi dataset. And you can see here that we have 4 different lines in the plot. The black one is a baseline in which we just use simple federated learning training with the Celebi dataset. Red one is the same as the black one, but with differential privacy. And the 2 other lines, the green and the blue, are PUFFLE with fixed lambda in the case of the green line, and tunable lambda in the case of the blue line. In these 2 cases, our fixed and tunable lambda, we use differential privacy and the mitigation of the unfairness. In this case, the target is 0.12, and this is a 6 here, but it's a 8% reduction from the baseline, and at the same time, in terms of disparity, it's a 25% reduction of the disparity, and at the same time, you can see here that compared to the baseline, we have an 8% utility drop. This is the first thing that I wanted to show. The second thing is that, as you can see here, and this result is similar in the other plots, the results that we have got with the tunable lambda is similar to the result that we have got with the fixed lambda. The difference is that, in our opinion, using the tunable lambda is easier because the parameters that you have to set are easier to interpret. So the methodology in the end is easier to use. I have some other results to show you, and I think that it's important to understand a little bit better these results because they are useful to understand the trade-off between the fairness and the accuracy. From left to right, we have 3 different levels of target level for the unfairness. We go from 0.12 to 0.04, and in the middle we have 0.09. These are 25% reduction of the unfairness, 50% reduction of the unfairness with respect to the baseline, and 75% reduction with respect to the baseline. And as you can see, the more we decrease the target, so the more we decrease the target, the more is the utility drop that we have, because without 25% unfairness reduction, we have an 8% utility drop. And then, for instance, with the lowest target, this 0.04, that represents a 75% accuracy unfairness reduction, we have a 17% utility drop in this case. So one important thing to highlight is that it's important to choose a target unfairness value that makes sense to have a model that has both a good utility and also a good fairness. But the thing that our method tries to do is to find a balance between them, because we are able to guarantee a big reduction in terms of unfairness while degrading a little bit the utility, but it's still a a utility drop that maybe we can still tolerate, considering the big reduction in terms of unfairness. So about I have some conclusion and some future work to discuss before the end of the talk. We have presented PUFFLE, and that is a method to train a model that can balance privacy, fairness, and utility by using a regularization approach. We consider it a personalized approach because the practitioner who wants to use this method has to set two requirements. One is a privacy budget, and one is a preference in terms of target model disparity that he wants to achieve. This personalized approach allowed us to introduce the tunable lambda that allows to have an easy to use method. And the experiment showed that for instance, using SELBA, we proved that we can have an unfairness reduction by at least 75%, while also having a decreasing inaccuracy by 75% in the worst case scenario. This is in the worst case scenario that we consider. About the future work, there are still a few things that we are developing now. We are considering a few other problems, and we hope to publish this in the next few weeks. One question that I'm sure someone will have is why you didn't use any other fairness metrics. We are working on this, and specifically we are working on using the error rate as an alternative fairness metric with that we want to introduce in this methodology. And we are also doing some experiments, and we will publish them soon with in a scenario with a distribution shift, because during the training maybe data could change, and so our method with the tunable lambda can adapt better to this scenario with respect to a method with a fixed lambda. The last thing, there is an assumption that we made in this paper that is the fact that basically the different clients in this paper that we published, the different clients are all unfair toward the same sensitive attribute. The one thing that we didn't consider is that the different clients could be unfair toward different attributes. And so this is another open problem that maybe we will try to solve in the future. So this is the end of my talk. I thank you again for having me today here. And if you want, this is the link to the QR code to the paper, and then there is also a QR code for the code that is published on open source on GitHub.
Great. Thank you, Luca, for the super interesting talk.
Thanks.
I have some questions. Some others in the audience, including you, Jan, have some questions, and feel free to, or if you don't have, think about them if you want. So my first question maybe is an obvious one. Maybe I think could be a question that some reviewers might ask is, if the practitioners have to set up the target unfairness level, how do they know what a good level is? Is it, I guess it's a single scalar, but what does it mean? Level 2 or level 8, and does this level change if suddenly I have a bigger pool of clients or a smaller pool of clients, or if I make my model bigger or smaller, those change what the target level should be?
Yeah, we were thinking about a target that depends on specifically on. So this target could depend, for instance, on regulations that are different in the different countries. This was one thing that we thought when we were discussing about this problem. And then it depends a lot on the scenario in which you are. For instance, if you already have a baseline, or you expect a certain value for the unfairness, maybe for the unfairness of the baseline model without any mitigation, maybe you can just say, okay, I want a reduction of X%, and just try to find a solution. If you want the other option is just to try maybe different levels and find a level of unfairness that can be acceptable for you and can be also good in terms of utility, model accuracy. But the main thing that we were also discussing, I think, in the paper, as far as I remember, was the idea of having a value that depends also on the regulations that you have in the different countries. About the change about a not tunable, but about a variable target during the training. We haven't experimented with this problem yet, but it's definitely something interesting to consider. We discussed about this when we were discussing about the idea of having a distribution shift, but we haven't experimented with this thing yet.
Yeah. Could you remind me briefly what is the definition of fairness you are using? I think you were presenting it at the very beginning.
Yeah, it was one of the first slides. So the one that we are using now is the demographic parity. And basically here what this metric wants is regardless of the sensitive attribute. So Z is a sensitive attribute here, and Y is the output of the model. Regardless of this sensitive attribute, the probabilities of having an output should be the same. There are a lot of other fairness metrics, and we are experimenting with the error rate that is similar to this one, but also takes into account the true label of each sample, basically.
Do you think that for this work, would it make sense to, in addition to this, maybe this being the main fairness metrics, also to consider, because the form of fairness I'm more familiar with are those that arise because of system heterogeneity, like some clients have much more data than others. Should that client with very little data, should it be ignored? Or no, maybe no, because it's a minority, and then if we never include those data points, then it would be unfair. I think this is something that could be captured with what you mentioned at the very beginning, like evaluate the performance, for example, of the global model with the error rate. I think what you meant by that is how the model behaves on each client's validation set.
Yeah.
Like that.
I didn't get what kind of data you were mentioning at the beginning of what you were saying.
I mean more in general, like how do you see this method address the fairness, but more that arises because of a system, because of the overall system, like maybe some clients are not always available. How do you handle that? Or some clients might have a lot more data than others. Should the clients that have very little data be being sampled more frequently, for example, so that knowledge is not forgotten by the global model? I know it's a different perspective to fairness, but I was just curious to see.
So about you're right about the amount of data. There could be some problem if you have some clients with a lot of data compared to others that maybe they have just a few samples. But we didn't consider too much this aspect in this paper. But it's something that we are more or less working also on this part. About the other thing that you were saying, we were also studying the local clients unfairness, and there are some plots in the paper that I didn't report in the talk, and we were trying to understand the relation more or less between the global aggregated model and the global aggregated unfairness and the client unfairness. But we didn't consider other aspects of the unfairness, like clients that are selected just a few times, because to simplify some things for the privacy, we decided to have a fixed number of client selection for each client. So we didn't consider this aspect.
Yeah, that sounds like a valid answer. I think it's impossible to test everything. So yeah.
Yeah.
Cool, perfect. I don't know if there is any more questions. Maybe any questions, Jan or Jan? No? Okay, well then, thank you very much, Luca. Again, just as I said for John, if anyone has a question, maybe if you're watching this later on YouTube, feel free to reach out to Luca. Probably you can reach out to him by email or maybe even in the Flower Slack.
Yeah. I mean, I'm also in the Flower Slack, so
Amazing.
yeah, I
Okay,
can
so
put
now,
link to the paper in the chat if someone is interested.
perfect. So this is the end of the Flower Monthly. We are super lucky that we ended with 2 fantastic talks and also another overview of the FlowerTune LLM initiative that is getting a lot of attention. It is the final Flower Monthly of the year, and the reason being is that usually we do it on the first Wednesday of every month, but the first Wednesday of January is January the 1st, and typically in most countries and territories it's public holiday, so we are going to skip it, and we'll do it in the second Wednesday, which is the 8th of January. So thank you once more to the speakers and to the audience, and see you in 2025. Okay. Bye.
Thank you, Javier. Again, Javier.
Thank you very much.
Thank you. Bye-bye. Bye.
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 Thank you.